Welcome to Week 9 Neural Networks and Deep Learning Fundamentals. This week, Day 1 will cover Introduction to Deep Learning and Neural Networks. Day 2 will be looking at forward propagation and activation functions. Day 3 we will cover loss functions and back propagation. Day 4 will cover gradient descent and optimization techniques. And on Day 5, we'll go over building neural networks with TensorFlow and Keras, followed by Day 6, where we'll be looking at building neural networks with PyTorch. We'll be looking at our neural network project, which will be image classification on Cypher 10. So let's get started with Week 9. Welcome to the Week 9, and today on Day 1, we're going to look at Introduction to Deep Learning and Neural Networks. Let's start with what is deep learning, and let's look at some of the differences between machine learning and deep learning. So first, what is deep learning? Deep learning is a subset of machine learning that uses artificial neural networks or ANNs with multiple layers, which deep architectures, to model and learn complex patterns in the data. Some of the key features include it automatically extracts relevant features from data, eliminating need for manual feature engineering. So whatever we did before, we don't need it. It's automatically done for you. So why did we do it? Just to understand the basics of it. Let's look at machine learning versus deep learning. So for example, we can compare features and see how it applies in machine learning and deep learning. So for example, feature engineering in machine learning is manual feature selection, whereas in deep learning, it's automatic feature extraction. For as compared to algorithms, machine learning has linear regression, SVMs, etc., whereas in deep learning, we have neural networks. For data independency feature, machine learning works well with small data sets, whereas deep learning requires large data sets. And for computation, it's computationally less intensive in machine learning, whereas in deep learning, it requires GPUs and TPUs for training. So some of the exercises that we will be doing might take much longer than usual to run if you are running on a simple machine. But if you have access to some of the GPU, TPUs machines online, cloud, you can probably run much faster. So let's go ahead and look at the overview of artificial neural networks or ANNs. The structure of a neural network has three layers. First is the input layer, which accepts input data features. And then we have hidden layers, which performs computations to extract patterns. And then on the top, we have output layer, which produces predictions or classifications. Some of the key components include we have neurons, which are the basic units of computation that take input, apply weights and biases, and produce outputs using an activation function. Then we have the weights and biases. Weights determine the importance of each input, whereas bias shifts the output of the activation function. And finally, what is activation function? It adds non-linearity to the model. Example, we have ReLU, sigmoid, tanh, and we're going to talk about these in future. Now, how neural networks work. So first, we have the forward propagation, where data flows through the network to generate predictions. Then we have loss calculation, where it compares predictions with actual labels to compute the error. And then finally, it does back propagation, where it adjusts weights and biases using gradient descent to minimize the loss. Let's look at some of the applications of deep learning. We're going to look at different domains and their use cases. First, in the computer vision domain, we have image classification, which is recognizing objects in images. Next, we have object detection. Example can be the autonomous vehicles. Next domain is natural language processing or NLP. There, we have text generation, example GPT models. You have used ChatGPT and others. We have sentiment analysis, which kind of tells if a particular text is positive, negative, or neutral. In the healthcare field, we have disease diagnosis. Example can be identifying tumors in X-rays. And another is drug discovery. Next, we have speech processing. In there, we have speech to text systems. Examples can be virtual assistants. And we have voice recognition. So based on all these, let's jump into hands-on exercise. where we will familiarize ourselves with common data sets in deep learning and set up an environment to work with TensorFlow and or PyTorch. We're going to use both, so I'm going to first show TensorFlow and then we're going to jump into PyTorch. So first step is to explore common data sets. We have MNIST, which is handwritten digit dataset, 28 by 28 grayscale images and 10 different classes. We have Cypher 10, which is 60,000 32 by 32 color images across 10 different classes. And we have ImageNet, which is a large data set for image classification with millions of labeled images. So we're starting pretty heavy on day one. So try to follow along with whatever I'm doing and pause wherever needed. So let's go ahead and start. I'm going to start a new file, Python, and save it in my day one underscore exercise. So let's start with getting some data from TensorFlow. So from TensorFlow dot keras dot datasets, import MNIST and Cypher 10. These are the two libraries that we're going to import. Now let's go ahead and load MNIST first. Now to load this, I am going to use our same type of method. Just follow along and we're going to explain later in more detail. Xtrain underscore MNIST, ytrain underscore MNIST. So this is one tuple. And then I have another tuple where I have x test underscore MNIST and y underscore test underscore MNIST equal to MNIST dot load underscore data. This is a function that is available inside MNIST where we can load the data and to training and testing modules. So now that we have it, let's look at how the data looks like. So I'm going to say f of MNIST data set train equal to x underscore train MNIST dot shape. So checking how big, how many rows, how many columns it has. And for test, let's see, x underscore test MNIST dot shape. I'll go a little slow just so that you can catch up with, because all these are new functions that we have. Now similarly for loading Cypher 10, I'm going to say x underscore train underscore Cypher, comma, y underscore train underscore Cypher, comma, x underscore test underscore Cypher and y underscore test underscore Cypher. Now this again from my Cypher library, I can just say load underscore data. Now we have this. I am going to go ahead and Cypher dash 10 data set, I'll say train data set equal to x underscore train Cypher dot shape, and for test I have x underscore test underscore Cypher dot shape. So I hope you got this. So again, for TensorFlow, you might have to open your terminal and install pip install TensorFlow. It might take some time. I already have it available, so that's why it went very quickly, but try to install it before you run it, or if you see any other issues, just install those libraries and it will be available for you. Now let's go ahead and run this. So I have this day underscore ex. So I think I forgot to put day one, but I'm going to go ahead and say Python day exercise.py. It's going to take some time because the data sets are really big. And as you can see, MNIST data set for training modules, we have 60,000 rows and 10,000 rows for this. Again, for Cypher, we have 50,000 Yeah, so these are images actually. If you think about it, 60,000 20 by 28 by 28 images, 10,000 28 by 28 images, 50,000 32 by 32 by 3, and then 10,000 32 by 32 by 3. As I mentioned, these are MNIST handwritten digit data sets, which are 28 by 28 grayscale images with 10 classes, whereas Cipher 10 is total 60,000 images with 32 by 32 color images. That's why 50,000 10,000, whereas this is 70,000 images. So I hope you got this working. Our second step is to set up a deep learning environment. So again, make sure that you run this pip install TensorFlow or it will not work for you. Now, next step is I'm going to go here and, or let's go up here. I'm going to say import TensorFlow as TF. And next, I am going to define a basic dense layer. So a layer is defined something like this. We can say TF dot keras dot layers dot dense, and then I can say units equal to 10 and activation equal to ReLU. So I have that. Next, I'm going to go print, say F tensor flow layer. I'll say layer. So that's it. So let's save this. And next, I am going to run this quickly. So we see this layer. I'm going to go ahead and say Python day and exercise, and it will give me again the data sets, and it will say TensorFlow layer dense layer built equal to false. So I have that layer displayed here. Perfect. Our next option is, what if I want to use PyTorch? In that case, I am going to go ahead and say pip install torch. That's what is used for PyTorch, and I need torch vision, which has all the libraries that we need to use. So it will take some time, but for me it's faster because I've already installed. And then I am going to go ahead and import torch here, that is PyTorch. And next I need some libraries from there, so I'm going to say import from torch dot I'm going to use nn torch nn module, which has all the layers and information on that, so I can create a layer using that. So for that, I am going to say define a basic dense layer in PyTorch. To do that, I'm going to say layer equal to nn dot linear in feature equal to in features equal to 10 and out features equal to 5. Perfect. And then I can go ahead and print f of PyTorch layer is layer. So this will show me the PyTorch layer. Let's go ahead and run it, and oops, not this. Go ahead and run my Python, and your output should look exactly same as mine, which shows the data sets, TensorFlow layer and PyTorch layer. So once you have this, let's go ahead and visualize the data set samples here. So that's the last step. So I'm going to go ahead. First, I'm going to import matplotlib.pyplot as plt for visualization. Now I want to first visualize my MNIST sample. So for that, I'm going to say plot.im show, and inside this I'll pass x train, and I'll use my MNIST data set at index 0, and I'm going to say cmap equal to, let's use grayscale for this, and then I'll give a title to this. Title, I'll say f MNIST label with y underscore train underscore MNIST of element 0. That's what I'm displaying. Next let's say plt dot show. So of that, I can do the same thing for let's visualize cipher dot 10 sample plt dot im show x underscore train, and I'll use cipher at index 0, and plot dot title is my data that it is, which is cipher dash 10. Label is y underscore train underscore cipher of 0. So what I'm pretty much doing is like that index 0 of train, we have the actual images, whereas in y train it tells me which image it is. So that's what I'm doing in both the cases. You'll see what I mean by when I run it. So I hope you were able to get all these things running, and you should be at the point where I am, where it will show you the MNIST dataset, Cipher dataset, show you the TensorFlow layer, show you that you could build a PyTorch layer, and then here is my dataset. It picked the number, so as I mentioned, it's handwritten numbers. For in this case, it's number 5. I can see it, and from the label, I can say that it is right. And for my PyTorch, it shows a label here, and it looks like it's a number 6 here. It says label is 6. That's what it's labeled as. So that's the Cipher 10 dataset. So I hope you were able to get all these things out here. If not, this is where you probably contact me or look up what's going on. If you have any issues or it shows up any errors here, let me know and I can get back to you quickly. So this will help you build your setup for the rest of the videos that we'll be looking at this week. So just to summarize today, we understood some of the core differences between machine learning and deep learning and how deep learning belongs to machine learning. We learned the structure and components of artificial neural networks, or ANNs. We gained insight into the wide-ranging applications of deep learning across different domains, and we developed some foundational skills to explore datasets and set up a deep learning environment. I hope you were able to follow along, and if you have any issues or have any questions, let me know in my messages and I'll get back to you. Day 2. Today, we'll dive into one of the topics that we learned yesterday, which is forward propagation and activation functions. So first, let's deep dive into understanding forward propagation. So what is forward propagation? Forward propagation is the process by which input data flows through the layers of a neural network to produce an output. It has input layer, which accepts input features and passes them to the next layer. Next, we have the hidden layers, which compute weighted sums of inputs, applies biases, and passes the result through activation functions. Then we have the output layer, which produces predictions typically using an activation function suitable for the task. So let's look at steps in forward propagation. First, you compute the weighted sum. The formula for that is z equal to w times x plus b, where w is weights, x are the inputs, and b is the bias. Then you apply activation function, which is a equal to sigma of z, where sigma is the activation function. Then you repeat this for each layer. Outputs of one layer becomes inputs to the next. It's pretty straightforward, right? Again, you don't have to worry about it because there's functions available that will do this for you. You just have to understand the basics. Next, let's talk about some common activation functions. For activation functions, we have the sigmoid. The use case for this is binary classification in the output layer. Its ranges is from 0 to 1, and limitation, it can suffer from vanishing gradients for large positive/negative z's. Next, we have the tan h, which is also called as hyperbolic tangent. The range for this is from -1 to 1, and the use case is its hidden layers where zero-centered outputs are preferred. The limitations for this are also prone to vanishing gradients, just like sigmoid. Then we have ReLU, which is rectified linear unit. It ranges from 0 to infinity, and the use cases are mostly commonly used in hidden layers due to simplicity and efficiency. The limitation of this is can suffer from the dying ReLU problem, which neurons are stuck at 0. Then we have softmax. Softmax produces probabilities summing to 1, and the use case for this, it's a multi-class classification in the output layer. Now, how do you choose which activation function do you want? So for depending on the layer, so example, if you're using in layer type hidden layers, Then relu or tanh is the recommendation activation function. In output, for binary data, you use sigmoid. For output in multi-class, use softmax. And output where regression is applied, you use none or linear. So let's jump into a hands-on exercise where we will be implementing forward propagation for a simple neural network in Python and experiment with different activation functions. So let's go ahead and open a new file. I'm going to say day 2 underscore exercise. Now here, first, let's go ahead and import our favorite library numpy as np. Next, let's define activation functions here. So let's see how do we build these activation functions or the definition. So definition for sigmoid, which takes an input of z, is, I'll just return directly, 1 divided by 1 plus exponential value of minus z. So that's how you define a sigmoid function. So just it's always going to be the same. This is the actual formula for it. 1 divided by 1 plus np, which is numpy.exp minus z. Next, let's do the hyperbolic tan, which is tan h, and it takes z as input. I'm going to return np dot tan h. So as I mentioned, you don't have to remember the formulas or use cases. They're all available for you in NumPy. Next, I'm going to use relu. For relu, you return np dot maximum, and that's here maximum 0 to z. That's the formula for relu, and that's the function that you use, maximum. Next, we have softmax. Now for softmax, the way you define this is exp of z equal to, this is a little bit complicated, where you say np.exp. This is the numerical, for numerical stability, we do this z minus np dot max of z. So that will give me exponential of z, and then I will return exp underscore z divided by exp underscore z dot sum of axis equal to 0 and keep dims equal to true. So this is the function. Now this is the formula for softmax. So these will never change, so you can use them, and in future we'll probably use some shorter methods of doing this. Now let's go ahead and implement the forward pass function. So I am going to say forward pass function in comment here, so we know what we are doing. The definition of forward pass underscore pass takes x, takes the weights, as I mentioned, all the different things that it will take, biases, and it needs an activation function underscore function. So this is how you define a forward pass. Now in here we need z, which is np dot dot, so multiplication of weights, as I mentioned in the formulas for forward pass, is w times x plus b, which is biases. So that's how we do it. Next, we need the value of a, which is activation function of the z above, and that's what we will return. Perfect. So that's our forward pass. Next, let's give some example inputs. In this case, I will say x equal to, let's create an array from np array, and I'll give the values inside here as 0.5, just to keep it simple, and 0.8 looks like, close it before, okay, there you go. These are my input features. Now I need my weights. For weights, I'm going to create an np of array again, and inside this I will give 0.2 comma 0.4 and 0.6 and 0.1 1. So these are my different weights that I'm using. Now for biases, I will say np dot array, and here I'm going to say 0.1 and 0.2. So these are my biases. So I have my input features, I have my weights and my biases. So once we have this, let's go ahead and perform the forward pass with different activation functions that we have defined above. So let's get all the activation that we have. So what are the different activations we have? For sigmoid, I have the sigmoid function, right? Next, for tan h, I have the tan h function that I've created above all these functions. Next, for ReLU, I have ReLU. There you go. Next, for softmax, I have softmax function above. So these are my different activation functions. Now, for I'm going to say go through this activation items. So I'm going to say name comma function in. So this is the name. This is the function in activations dot items. So I am looping through or iterating through each and every item here, and I'm saying output of those equal to forward pass, passing the x, passing weights, passing biases, and passing the function, which is the activation function it needs. And I'm going to say print f of, depending on the name, like which activation function I'm using, say activation output. So let's say sigmoid activation output is go to new line and say whatever the output is slash n. So it will go one at a time and display as the output. So let's go ahead, save it, and let me run it here. Python day2 exercise.py, and there you go. We have the sigmoid activation output, we have tan h activation output, ReLU activation output, and softmax activation output here. Now, what is the fun in just looking at numbers when you can visualize them? So I'm going to go ahead and import matplotlib.pyplot. I always like to import, I keep my imports on the top, but just for now, I'm going to use it here just so we can go in flow. And I am going to define range of inputs here. Let's say z equal to np dot linspace minus 10, 10, and 100. So I'm trying to visualize the activation functions here. So for that, let's go ahead and say, let's plot activation functions. So I'm going to say plot dot figure size, come on, fig size equal to 12 comma 8. So I think big enough for us to see. plt dot plot, and I'll give the value of z that I've above, and I'll for y I'll use sigmoid.z for the first one. I'll say label equal to sigmoid. Next, I'm going to do it for one tan h, ReLU, and activation. Oh, sorry, tan h and ReLU. So next, I'm going to say plot tan h, label equal to tan h. Next, I'll use ReLU of z and label equal to ReLU. And my last one is softmax. Softmax label equal to softmax. So I have all the 4 plots here. Next, let's go say plot dot title, and for the title I'll give activation functions. Next, I will say for x label I will use input is z, and for y label, I'll say it's output. Next, I'll show the legend because I've given labels to everyone. So show that legend. You want to see a grid, I can also display a grid and say that display it true, and finally show the plot. So save it. Now I'm going to go ahead, clear it out and run it. And there you go. We have all our four sigmoid. We have tan H, ReLU and softmax all displayed over here as per our code here. And if you do not see something similar to this, depending on your data range that you have given here, uh, just let me know. If you see something different, please send me in my message. If you see any errors, do let me know and I'll get back to you as soon as possible. So from this, what we have done is we have gotten the forward pass where we observed how weights, biases, and activation functions influence the output of a neural network. We looked at different activation function behavior. We visualized the and compared the characteristics of common activation functions. And based on this, you can choose the appropriate activation function for different layers and tasks that you will be working on. So just to summarize, today we understood the forward propagation process in a neural network. We gained knowledge of commonly used activation functions and their mathematical formulas. We developed an intuition for selecting activation function based on the task requirements, and finally gained some practical experience implementing and experimenting with forward propagation and activation functions. If you had any problems while implementing this, let me know. If you have any other questions, do get back to me on my messages and I'll get back to you as soon as possible. Day 3, loss functions and back propagation. Yesterday we looked at forward propagation. Today we're going to look at both loss functions and back propagation. So first, let's understand loss functions. What are loss functions? Loss functions quantify the difference between the predicted output of a model and the actual target value. They guide the training process by providing a metric to minimize during optimization. What is their role in neural networks? First is error measurement. They evaluate the accuracy of predictions, and they also give feedback for optimization, where provides gradients for weight updates via backpropagation. Now let's look at some of the common types of loss functions first. We have mean squared error MSE, commonly used for regression tasks, and it penalizes larger errors more heavily than the smaller ones. Then we have cross entropy loss, which is used for classification tasks, and it measures the difference between true labels and the predicted probabilities. Next, let's look at introduction to backpropagation. What is backpropagation? Backpropagation is the process of computing gradients for each weight and bias in a neural network, enabling optimization algorithms like gradient descent to minimize the loss function. The steps involved in backpropagation are: first is a forward pass where we compute the output and loss for the current weights. Then is the backward pass, which calculates the gradient of the loss with respect to each parameter. And then is a weight update where we use the gradients to update parameters. Some of the key concepts include: we have the gradient, which is the rate of change of the loss with respect to a parameter. We have gradient descent, which is an optimization algorithm that minimizes the loss by updating parameters in the direction of the negative gradient. And we have been through gradient descent before in earlier weeks. Now, with this back of our head, let's start with hands-on exercise where we will be implementing a basic loss function. We'll calculate the gradients manually and visualize the effects of different loss functions. So let's go ahead, start with a new file, call it day3 underscore exercise.py. Start with import numpy as np. Then let's get the mean square error MSE loss. Oops. The way to define this function is I'm going to say MSE. Define MSE underscore loss y underscore true and y underscore predicted values. That's what it takes as input, and this will return np. So MSE is nothing but mean of y underscore true minus y underscore pred squared 2. So that's how we define MSE loss. So once we have that, next let's go ahead and do the binary cross entropy or BCE loss function. To define this, I'm going to say binary cross entropy loss. Again, it takes the same y underscore true and takes y underscore pred as input parameters, and it does some manipulation with y underscore pred where you can clip y underscore pred. This is like preventing log of 0, that's why we do this, and we give 1 e raised to minus 15, 1 minus 1 e minus 15. So this is how you define the ypred, where you prevent log of 0. Next, I'm going to return minus np dot mean of y of true times np dot log of y pred. So now you see why we did that preventing log of 0 in the previous step, because of this. And then we say 1 minus y of true, let me show you this, times we say np dot log 1 minus y of pred. Make sure it displayed properly. So this is the actual formula for BCE loss, which is binary cross entropy. Now let's take some example data. Y of true equal to, I'm going to create an array for this data, where I will say the true values that we got was 1, 0, 1 and 1. Now the predicted value that were created for these were, let's say, np dot array, and for the first one is 0.9. I'll keep it as close to the values above as possible, 0.8 and 0.7. So if you see 1011, predicted value is 0.9, 0.2, 0.8 and 0.7. So now let's do the calculation of loss here. I'm going to say MSE equal to MSE loss, and to this I'll pass y underscore true values and y underscore pred values. Same thing for BCE. I will say binary cross entropy function that we created, and we'll pass y true and y pred. There you go. So that's calculates the loss, and let's display this out so we can see what these values are. MSE loss is MSE, and I'll say 0.4 f. Want to see the entire number for binary cross entropy loss. I will say BCE 0.4 f. So let's go ahead and look at these. I'm going to say Python day 3 underscore exercise, and here we go. We have MSE loss of 0.04 and binary cross entropy loss of 0.22. That's how you calculate the loss functions. Now let's go ahead and calculate the gradients manually. So what I'm going to do is I'm going to create a derivative of MSE loss. This function I'll call it DF MSE gradient, and this will take the same values y true and y pred as input, and this will return back 2 times, this is the formula for that, y underscore pred minus y underscore true divided by the length of y underscore true. So this is the formula for MSE gradient. Next, let's create a derivative of BCE loss. To do that, I'm going to go move up a little bit and I'll say DEF BCE gradient. This also takes the same parameters. And the formula for this is again to prevent division by 0, I am going to make sure ypred equal to np dot first clip y underscore pred to 1 e minus 15 and 1 minus 1 e minus 15. Let's see if I got everything right. Yes, that's the formula to prevent division by 0. And then I will return y underscore pred minus y underscore true divide by y underscore pred times 1 minus y of pred. There you go. So that's the formula for BCE gradient. So I have that. Now let's go ahead and calculate the gradients. So I'm going to say gradient of MSE equal to MSE gradient, and I'll pass the same y true and y pred that we have initialized right here, the example data we have. Similarly for BCE, I will call the BCE gradient function, and here I'll pass y true and y pred. Let's go ahead and print this out to check MSE gradient, which is grad underscore MSE, and similarly BCE gradient is grad underscore BCE. Let's look at these. And there you go. We have binary cross entropy loss, MSE gradients, MSE loss here. We have MSE gradients is minus 0.05, 0.1, minus 0.1, and minus 0.15. For BCE gradients, we have these are the values depending on the inputs that we have provided. If you look at them, they're very close to the values there. Perfect. So this is how you calculate the loss and the gradients. Now let's go ahead and visualize these effects on the of loss function. So let's go ahead and draw some graphs. To do that, import matplotlib dot pyplot as plt. Oops. Next, I am going to go ahead and define my predictions and true labels. So for predictions, I will say np dot linspace and say 0 to 100 of them. True label true underscore label equal to 1, which is the fixed label that we are setting here. Next, I am going to go ahead and compute the losses. To compute the losses, I'm going to say MSE losses equal to true label minus p squared for p in predictions. So for all these predictions, I'm getting the MSE losses. Then next, I'm going to say BCE losses equal to, in this case, minus true label times np dot log of max of p comma 1e minus 15 minus 1 minus true label times np dot log of max, again 1 minus p this time, comma 1e minus 15 for p in predictions. Okay, I hope I got the formula right. Minus true label times np log max p 1e minus 15 minus 1 minus true label np log max 1 minus p 1e minus 15 for P in prediction. So perfect, looks good to me. Let's go ahead and do the plot now. So I'm going to say plot for this is plt dot figure, where I will specify the fig size equal to 10,6. So how big my plot needs to be, or my graph is to be, dot plot. First, let's do predictions, and then next to it MSE losses, and then label here I will specify as MSE loss. Next, for my predictions with along with BCE losses, label equal to binary cross entropy loss. I like to have my full name displayed. PLT dot title, I will say loss functions comparison, and then PLT dot, I mean, based on the numbers that you have seen, you probably already have it in your mind of how it looks like, but it's always good to see it in graph. Y label is loss, PLT dot legend, PLT dot create a grid, and PLT dot show. So this will plot our graph. We clear it out, run it again, and there you go. Here the prediction from 0 to 1 for both binary cross entropy and for MSE loss. This is exactly what I expected, and that's what we get. Let me know if you were able to follow along and get through this exercise. If you have any questions, do let me know in messages and I'll get back to you. So just to summarize, today we gained a foundational understanding of loss functions and their role in training neural networks. We learned the mathematical formulations and applications of MSE and cross entropy loss. We developed an understanding of backpropagation and gradient calculation. And finally, we gained some practical experience implementing these loss functions and manually calculating the gradients. We'll not have to do this, but this is a good exercise to understand how all these works in the background. If you have any questions or had any issues implementing these, let me know and I'll get back to you. Day 5, Building Neural Networks with TensorFlow and Keras. Today, we're going to go over first introduction to TensorFlow and Keras for deep learning. What is TensorFlow? TensorFlow is an open source library for numerical computation and machine learning. It provides tools for building and training deep learning models. What is Keras? Keras is a high-level API integrated with TensorFlow that simplifies the process of creating and training neural networks. Now let's look at some of the key features of Keras. It's user-friendly, it's intuitive syntax for rapid prototyping. Modular, which is building blocks for defining layers, optimizers, and loss function. And as per integration goes, it's compatible with TensorFlow and scalable deep learning tasks. Let's look at defining layers, models, and compiling networks in Keras. So first, let's look at defining layers. Layers are the building blocks of neural networks. Common types include, we have dense, which is fully connected layers, and where each neuron is connected to every neuron in the previous layer. Then we have the dropout layers. It randomly drops connections to prevent overfitting. Then we have the activation layers, which applies activation functions to introduce non-linearity. Now let's go ahead and build models. Keras supports two primary ways to define models. One is sequential API, which is a linear stack of layers. And then we have the functional API, which is more flexible and allows for complex architectures. Next, talk about compiling a model. This specifies optimizer, which is algorithm to update weights. Examples are Adam or SGD. Then loss function. This is a metric to minimize during training. Example can be cross entropy. And then we have metrics for additional performance measures. Example can be accuracy. Next, let's talk about training, evaluating, and saving a model. Now for training, you can fit the model to data using model.fit. For evaluation, you can test the model on unseen data using model.evaluate function. And for saving and loading, you can save a trained model using model.save and reload it with keras.models.load model. With all this knowledge, let's jump into our hands-on exercise where the objective is to build, train, evaluate, and save a simple neural network to classify digits from the MNIST dataset. So our step one is create a file first, save it as day5 underscore exercise, and here we'll load and pre-process the MNIST dataset. So I'm going to import TensorFlow as TF. Next, I am going to take from TensorFlow dot keras dot datasets. I am going to import MNIST dataset. Oops. Next, I am going to go from TensorFlow dot keras dot utils. I am going to import to underscore categorical. So these are the libraries that I need. Now let's go ahead and load the MNIST dataset. Load MNIST dataset. To do that, I will have x underscore train, y underscore train. We'll have another tuple of x underscore test, y underscore test equal to, go to MNIST and say load the data. So this will load my data in these parameters, these variables here. And now once I have that, let's go ahead and normalize the data. X underscore train equal to x underscore train dot reshape that from -1 to 28. These are the size of the images. 1 dot as type float of 32 divided by 255.0. Same thing I'm going to do with my x test data. I'll take the x test data, reshape it -1 28 28 as type float of 32, because the whatever data we get, I have rows and then /28 by 28 image size, and that's what I'm converting into as type float 32 and have that available. Next, let's add the one hot encode the labels. So we have y underscore train. These are the labels that tell you what numbers they are, which are returned. So I'm going to convert that to categorical. Whatever y train we have, 10, and then same thing for y test. So there you go. So it's converted now. So we have encoded the labels. Now let's go ahead and print and see how does it look like. Training data shape is x underscore train dot shape, test data shape, test dot shape. Just let's to confirm, let's go ahead and run python day5 underscore ex dot py. It will download that data set, and it looks like I have misspelled utils. Clear it out, run it again, and we have the data set. Now we have it in proper 60,000 2021, 10,000 2021 for the test data shape. So we have everything that we need. Next thing that we need to do is define a neural network. So I am going to take something from the models that are available. So first let's get we need the sequential model from TensorFlow dot keras dot models. I want to import sequential. Now this module contains tools for building neural network models, and sequential is a linear stack of layers. It allows you to add one layer at a time, going from input to output sequentially, and that's what we are going to use. Next, I'm going to say from TensorFlow dot keras dot layers, I want to import dense. Now, this so from TensorFlow Keras layers, which provides building blocks for layers in a neural network, we are importing dense, which is a fully connected layer where each neuron is connected to every neuron in the previous layer. So that's what dense does. Next, I'm going to use flatten. Now, flatten is something that flattens a multi-dimensional input into a single vector for fully connected layers. So that's why I'm using flatten. Conv 2D. Now this is a 2D convolutional layer that applies filters to the input image to extract features. So that's why I'm using that. Next one I'm going to use is max pooling 2D. Max pooling 2D reduces the spatial dimensions of the input while retaining the important features. So it's used for downsampling. And then finally, I will use dropout. This is a regularization technique to randomly set a fraction of the input units to 0 during training, preventing like overfitting. So now I'm going to go here and first let's create the model. So I'm going to say or build the model. So for model, I'm going to say model equal to sequential. Now, this initializes a sequential model. Layers will be added sequentially here. So I am going to create a subset. Okay, there you go. The first thing that I want to add a conv 2D, which is the 2D convolutional layer. So I'm going to say conv 2D, and then I need to pass 32, which is number of filters. These are learnable feature detectors. Next parameter that it takes is 3 by 3. Now this is the filter kernel size, meaning each filter is a 3 by 3 matrix. Next I want is activation equal to ReLU. So here I'm setting activation equal to ReLU, which means it applies the rectified linear unit ReLU activation function, which sets negative values to 0, introducing non-linearity. And I am going to say input underscore shape equal to 28 comma 28 comma 1. So this specifies the shape of the input image, which is 28 by 28 pixels with one channel, which is the grayscale, which is what we have created above. So that's what I'm specifying here. Now next, oops, I think comma. Next I want to do is use the max pooling 2D and pass it to comma 2. What I'm doing here is I am saying to add a max pooling 2D layer with 2 by 2 pool size, meaning it reduces each 2 by 2 block in the input to a single maximum value. This reduces the spatial dimensions by half. Next, I'm going to flatten everything. This pretty much adds a flatten layer to convert the 2D feature map output of the previous layer into a 1D vector. Necessary for this is necessary for connecting convolutional layers to fully connected layers. So now that we have that, I'm going to use a dense layer 128 comma activation equal to ReLU. Here I am adding a dense layer with 128 neurons and I'm setting activation equal to ReLU, which applies the ReLU activation function. Finally, I'll say dropout 0.5. What this does is it adds a dropout layer. 0.5 is the fraction of neurons to randomly drop during training, helps prevent overfitting. And actually, this is the final step. Dense 10 comma activation equal to softmax output layer for the classification. So this adds the final output layer. 10 neurons is corresponds to the 10 output classes, example digits 0 to 9. If this because we are using the MNIST data set which have 10 different digits, that's what we are using here. And activation softmax outputs a probability distribution across those 10 different classes. So finally, let's go ahead and display model architecture. This I can do by saying model dot summary. This displays the model architecture showing each layer type, output shape, and the number of parameters also total number of trainable and non-trainable parameters in the model. So that's what this does. Let's go ahead and run this just to play around with it. I'm going to go here, run it, and there you go. It did all the things and it gave me my layer definition here. If you see con 2D, max pooling 2D, flattened, dense, dropout, and dense one, and it showed you all the output shape from it and gave you different parameters numbers here. Total parameters is these many parameters are used. Trainable parameters are these, non-train. So it gives you a summary of the entire model that we have created. Now let's go ahead and compile the model. So I'm going to say compile the model, and then I'm going to say model dot compile. Now what do I need to pass to this? I need to use optimizer. Which optimizer I want to use is Adam optimizer. I want to, for loss, I want to use categorical and cross entropy. Next, for metrics, I want to use accuracy. Perfect. So that will compile my model. And now let's go ahead and train the model. That's our next step. Train the model. So I'm going to say history equal to model dot fit, and inside here I'm going to pass x underscore train, y underscore train, also other parameters, how many epochs I want to train it for. I'm going to say 10 epochs. Batch size I want to use equal to I'll say batch size of 32, and then validation split that I want to do is 2080, so 0.2. That's what I'm going to set here. So this will train the model. Next, let's go ahead and evaluate the model. To evaluate the model, I am going to say evaluate first the model. For that, I can just get the test loss. I can get test accuracy of this model by calling a function called as model dot evaluate. So with the TensorFlow, we don't have to do all the other things that we used to do before. It's pretty straightforward. We just call model dot evaluate, and I can print now test accuracy is test underscore accuracy 0.4f. Perfect. Now let's go and save the model. Let's see how we can save this model and also reload this model if you ever want to reload this trained model. So once you're done training, it's always a good idea to save it so you don't have to go through this step again and again. I'm going to call this mnist underscore classifier dot h5. That's how I'm going to save this model as. Now if you want to load this model ever again in some other code, so say let's say you train this and now you want to use it somewhere, you can just say from TensorFlow dot Keras, so you don't have to do this training every single time. I mean, that's how it works. Once you train the model, you load it into your application and you make sure that, okay, let me fix import load model, and then you use this model over and over again in your production application. Loaded model equal to load model. I'm going to give the name that I saved it as. Okay, next I am going to verify loaded model's performance. That's another thing that you have to kind of cross check if the loss and accuracy is same as what we got earlier, because it's the same model. Evaluate x underscore test and y underscore test, because that's the data set that I have. I'm going to say print f loaded model accuracy is 0.4f. Oops, sorry. Need to first give the accuracy 0.4f. Perfect. That's the entire code that we have here. So let's go ahead and run it, clear it out, run it all over again. So we'll see the summary, we'll see all the things that you've done here step at a time. So my summary, now it's going here again here, and it's going to run through 10 different cycles to train the model. So I'm going to give it a little pause and come back to it once it's done. So it took some time and went through all the 10 epochs. And as you can see, every single time the loss is changing here for each and every iteration. We have the accuracy changing and getting better every single time. And our test accuracy finally is 0.9871. And then it saved the model. And then I loaded the model again. If you open this particular folder, we'll see that we have the MNIST classifier H5 saved here. It's around 8.4 MB size, and then I loaded that model and then tested the accuracy. It's still the same thing, 0.871, because I'm giving the same data to it. So that, there you go. This is how you can create a model, train a model, evaluate, and then finally save it into your hard disk. And then next time when you're working on a project, you can load it directly from there, or you can also serve it on cloud and then write some APIs around it to use this particular model. So just to summarize, today we understood how to define and compile a neural network in Keras. We learned to pre-process data for deep learning models, and we gained experience in training, evaluating, and saving a deep learning model. Finally, we developed some practical skills in working with MNIST dataset for image classification. I hope it was helpful and you were able to follow along. If you had any issues in installing or writing this code, if you have any other questions or any suggestions, let me know in the messages and I'll get back to you. Day 6. Building neural networks with PyTorch. Yesterday we did something similar with Keras. Let's see how you can do this with PyTorch today. First, let's go ahead and introduce PyTorch and its core components. Now, what is PyTorch? PyTorch is an open source deep learning framework that provides flexibility and dynamic computation for building and training machine learning models. Some of the core components of PyTorch include, we have tensors, which is multidimensional arrays, similar to NumPy arrays and with GPU support for accelerated computation. We have AutoGrad, which are automatic differentiation engine that computes gradients for optimization. And then we have Torch NN module, which we've used already, which provides tools to define and train neural networks with layers, activation functions, and loss function. Let's talk about building a neural network in PyTorch. The steps that we will follow is, first we'll define the model. We use torch nn.module to create a neural network with layers and forward propagation. Next, we're going to define the loss function. We'll use built-in loss functions like cross entropy loss. Then we'll define the optimizer. We'll use optimizers like SGD or Adam for weight updates. Next, let's talk about training, evaluating, and saving a model in PyTorch. For training, we will use forward pass to compute predictions. Next, we're going to compute loss and gradients using backpropagation. And then we will update the weights using an optimizer. For evaluation, we'll test the model on unseen data and calculate metrics like accuracy. Finally, saving and loading. We'll save the model's parameters using torch.save and load them using torch.load. Now let's jump into our hands-on exercise where our objective is to build, train, and evaluate and save a neural network for MNIST digit classification using PyTorch. So our step 1 is to load and pre-process the MNIST dataset. For that, I'm going to go ahead, create a new file, save it as day6_ex, and here first let me import Torch. This is the core PyTorch library for tensor operations and deep learning. Next, I'm going to say from Torch Vision, I am going to import datasets and transforms. So here, Torch Vision.datasets provides popular datasets like MNIST, which we'll be using, and also it has Cypher 10 if you want to use. The Torch Vision transforms provide transformations for pre-processing data, example converting to tensor and normalizing. And finally, we'll use from torch.utils.data import data loader. So this data loader is a utility to handle data batching, shuffling, and loading in parallel. So next, let's go ahead and define our transformations. So I'm going to say transformation equal to transforms dot compose, and here I will say transforms dot to tensor. That's the function that I'll call. And next I'll say transforms dot normalize, and I'll pass the value 0.5 comma 2 comma 0.5 comma. So what I'm doing here, so the transform.compose, it combines a list of transformations to be applied sequentially. So first I convert by calling the to tensor, I'm converting image data into PyTorch tensors, which scales pixel values to 0 to 1. Next, I am normalizing tensor data to have a mean of 0.5 and a standard deviation of 0.5 for better training stability. And that's what this 0.5, 0.5 is here. Now, next step is to load the data sets. So I'm going to go ahead and say load data sets. I need the training data set equal to data sets dot mnist root equal to dot slash data train equal to true transform equal to transform that we created above, and download equal to true. So here let's make sure, okay, this is, I've saved it as transformation. I don't know why. Transform is what I wanted to save it as. Perfect. So there you go. So what I'm doing here is I'm downloading the mnist data set. Root equal to dot slash data is the directory to store the data set. So it will create a folder called as data and save it there. Train equal to true or false, which specifies whether to load the training or testing set. And transform equal to transfer applies the defined transformations to the data set. And download equal to true, it downloads the data set if not already present. So next thing is same, this is for the training data set. Now I'm going to say next for test data set mnist root equal to dot data, and here not for training, it's for testing, so I'm going to say false, and download equal to true. Perfect. So that's what I'm going to say here. Our next step is to create the data loaders. So I'm going to say create data loaders. Now I'm going to create a train loader equal to data loader. I have that imported. So I'm going to say train data set is what I'm going to pass it. Say batch size equal to 32 and shuffle equal to true. So what I'm doing here is the data loader function loads data in batches for training and testing. So when I say batch size equal to 32 is the number of samples per batch. Shuffle equal to true, it shuffles the training data to ensure randomness. So if I set shuffle equal to false, which is in my test loader, data loader, I'm going to give the test data set, and I think make sure that there's no typo. Batch size 32, shuffle equal to false. It keeps the test data in order for evaluation. So that's what it does here. Next, let's go ahead and print our training data size to see how does it look like. This will be length of train underscore data set. Similarly, I can do the same thing for test data set, where I'm saying test data set length. I'm going to go ahead and open my terminal, and I'll say Python day 6 underscore exercise, run it. And since it's not been downloaded, it's downloading it first time, and it's going to save in my .data folder. and it says training data size is 60,000 and test data size is equal to 10,000. If it can't find the data set, it'll try the next one and try to download it from there. So you don't have to worry about that. I'm going to clear it out. If I run it again, you see it doesn't download it again because it's already downloaded it. I can open this and check the data folder, and you'll see the MNIST data set is available right here. Perfect. I'll close this, go back here, go back to our coding. Our next step is to define the neural network. So to define the neural network, what I'm going to do is I am going to go ahead and first import torch.nn as nn. Next, I will import torch.nn.functional as f. So this torch.nn module provides classes and functions for building and defining neural networks. It contains predefined building blocks like layers, loss functions, activation functions, and more. The alias nn is used for convenience to access these components more easily. And then I'm doing the same thing for functional, where this module kind of contains functions for operations that can be applied directly without defining them as layers. These are stateless functions, meaning they don't have parameters that need to be learned like weights or biases. And it's commonly used for applying activation functions or loss computation directly. And we'll probably see how we are going to use them in the following code. So go ahead and first, let's say here, I am going to define the model. For this, I'm going to create a class called as neural network, and I'll pass nn.module to it. So nn module, what it does is it creates the base class. It's the base class for all PyTorch models, and that's what I'm doing here. And then I am going to override or define the initializer method init underscore self. Now here I am going to call the super method first, which is neural network, and pass self object and call the initializer method of that init underscore. That's how we call that. Next thing that I'll do is I will say the flatten function or flatten layer equal to nn dot flatten. So this flattens the 2D image 28 by 28 into 1D vector. So that's why we're using this. Next, I'm going to say self dot fc1 equal to nn dot linear. This is my first layer. So I'm going to say linear 28 times 28 comma 128. So this is what I'm creating is input size is in this particular case is 784, which is the 1-day vector from my flatten. So I am saying that flatten that into a size of 128. That's what I'm doing here. Next, I'm going to say self dot fc2 equal to my second layer. I am saying linear 128 comma 64. So whatever the input that comes from this 128, I am changing that to an output size of 64. Next, I am going to create another hidden layer, and I'm going to say nn dot linear, and the 64 I'm going to convert that into 10. So this is an output size in 10 for 10 different classes that we have for numbers. Next, we're going to define, as I mentioned, the forward class. So I'm going to say forward function. So say self comma x in here. So this is for forward pass, where I am going to say x equal to self dot flatten, whatever that function above is, and pass x to it. Next, I'm going to say x equal to f dot value. As I mentioned, f is used for all the different activation functions. So first I'm going to say self dot fc1 of x. Next, I'm going to say value self dot fc2 of x. Then x equal to self dot fc3, the output layer, x, and then return the value of x. So this f dot ReLU, it applies ReLU activation to introduce non-linearity in this particular case. And finally, we'll go ahead and initialize the model. I'm going to say model equal to neural network, and if I want I can print the model, but we'll probably see this later. So this is your entire code to define the neural network. Now the next thing is we are going to go and define the loss function and the optimizer. So for that I am going to say, as I mentioned, define loss function and optimizer. For this I will say the criterion equal to nn dot cross entropy loss and optimizer equal to torch dot optim dot, as I mentioned, SGD or Adam is what I'm going to use. So I'm going to use Adam this time, and I'm going to say model dot parameters. I'll pass the first the parameter, which is model dot parameters, and LR learning rate equal to 0.001. So what I've done here is the criterion is the loss function where I'm using cross entropy for multi-class classification, and which because we have 10 different outputs here. Optimizer, we are specifying Adam optimizer for updating model weights, and learning rate I'm specifying it to 0.001. Next step is to train the model. So for training the model, I'm going to create a function. We'll call it training loop. Let's move it all the way to the top. Say function, and I'll say train underscore model, and the parameters that it needs is it needs model, it needs the train loader, it needs criterion. I'm gonna just copy this. I need optimizer, and I need epochs. If I've not specified any epochs, I'll just run it for 5. That's what I'll set as default, and I'll say model dot train here first. Model.train puts the model in the training mode. Now I can run the epochs. Run epoch in range of epochs. Yes, there you go. Now what I'm going to do is I am going to uh, put a running loss, create a variable called as running loss equal to 0.0. And then once I have that set, I'm going to say for images, comma, labels in train loader, because that's where my training data is. So this iterates through batches of the training data, and first I'm going to go and do the zero gradients, where I'm going to say optimizer, I want to do a 0 underscore grad. This resets all the gradients first. Next I'm going to say, so for each and every image it will go ahead and do that. Next is forward pass, where I'm going to say outputs from this forward pass equal to model images. So this performs a forward pass, as I mentioned. Next I have loss equal to, this will calculate the loss. I'm going to use the criterion and pass it outputs and labels. Next I want to do the backward pass and optimize. So I will, let me write that, backward pass and optimize. Oops, caps lock got on, and optimize. So here I'm going to say loss dot backward. So this will compute the gradients for back propagation, and then finally I'll say, not finally but optimizer dot step. This will update the model parameters, and then now the running loss that I've created above, I'm going to increment that to loss dot this particular item, and then I can print here, just for display purposes, our epoch is epoch plus 1, increment that to 1, and loss is running loss that we are incrementing, divide by length of train loader 0.5. for F. So running loss distracts the loss for each epoch and updates it, and then finally we do this. Now we have this. Now let's run this because this is just a function. So I'm going to go outside and I'll say train the model, and now I'll pass all the parameters that we already have. We have model, we have the trained loader, we have criterion, we have optimizer, and epoch. I will, and let's just see one more, epoch equal to 5. I'll leave it the default of 5 times. So this will train the model for 5 epochs. So once that is done, our next step is to evaluate the model. So I'm going to go, before even running it, let's write the code to do the evaluation loop. Again, I'll write a function. I'm going to say evaluation underscore model, or evaluate underscore model, and this needs our model and it needs our test loader. Now here to evaluate it, I'll say model dot eval. Oops. Just like model dot train, model dot eval puts the model in the evaluation mode. Next, I'm gonna create some variables, correct equal to 0 and total. I'll tell you why these are in a second. Total equal to 0. Now with torch dot no underscore grad. So this disables gradient computation for efficiency, and with that on, I am going to go over the images and label in my test loader, and I'll first calculate the outputs, which is model of images. Next, I will say underscore comma. I will get the predicted. The first one is because it gives me 2 different parameters and I don't care about the first one, so that's why I've used underscore max outputs dot data comma 1. This will get me the class with the highest probability, so that's what I want. Next, I'm going to say total plus equal to labels dot size, so I'm going to save that for this particular iteration, and then correct plus equal to predicted equal to labels. If it's right predicted, I am going to say sum dot item. Keep on adding them, so that's why I am incrementing it. Next, let's go ahead and print f of test accuracy. Oops. 100 times correct divide by total 0.2f. So that will give me my percentage value. That's why I multiplied with 100. And finally, let's go ahead and evaluate the model, pass the model and the test loader. Perfect. So I've passed those, so that will, now we can do save also, but yeah, let's go ahead and save first before even doing the next step. So as I mentioned, it's always better to save the model and see how we can save it. So I'm going to say torch dot save. So there's a built-in function as I mentioned, and I can say model dot state underscore dect. That's where my model is available. I'm going to say the model name is mnest underscore model dot pth. Since it's PyTorch, I'm going to save it as pth. And if you want to reload the model, again, the loaded underscore model equal to neural network. I'll initialize that, and I'm going to say loaded underscore model dot load underscore state underscore dect, and I can just use torch dot load and whatever I've saved it as dot pth file. Perfect. So that's how you can load it. Now if you want to verify it, verify the loaded model performance just to make sure that it's fine. You can always call the evaluated and then get the loaded model and use the same test loader to test it out. So that's does take care of it. Now if you want to experiment with model structure and the learning rate, you can always update the optimizer. I'm going to just write this code, but I'm not going to run it. Optimizer with a new learning rate. You can just say optimizer equal to torch dot optim dot adam and pass model dot parameters. That's what we did earlier. And learning rate equal to, this time I want to increase one more decimal, 0.0001, and then I can say train underscore model, pass it the model, pass the train loader, and then we need criterion, and then we pass the optimizer for epochs. I'll keep it the default 5, and then you can evaluate the model again and call that model comma test loader. Now if you want to try this out, you can try it out, but I am not going to run this because this will work, of course, because we have this earlier too. So I'm going to save this, go back and clear it out and run it again. Oh, looks like I have a error. Instead of nn.module with a capital M, I am using a small m. Perfect. Let's go clear it out, run it again. And there you go. We have the training data size, test data size, neural network, and now it's going through the epochs and printing it out. It's going to take some time to display all the epochs, so I'm going to just pause it here and then come once it's done and and talk about the output. I realized we only ran it for 5 epochs, so it didn't take much time. We were almost done. But as you can see here, it gave me the loss for the 5 epochs. It gave me the test accuracy of 96.92. And after I saved, I mean, it's giving me a warning for whatever I'm loading and saving and loading, but that's fine. You can ignore that. And once I load it, I see the test accuracy is exactly same as because it's the same model that I'm saving. And if I open this particular folder, you'll probably see that I have the MNIST model right here saved. I have my data from MNIST right here. So this is perfect. I hope you have the same experience here. If you don't, if there was an error or issue that is an error, not a warning, let me know in the comments and I'll get back to you. But just to summarize, today we went and understood PyTorch's core components, the tensors, AutoGrad, and NN module. We gained hands-on experience building and training a neural network in PyTorch, and we learned how to evaluate and save PyTorch models effectively. And finally, we developed intuition for experimenting with model architectures and hyperparameters. So if you have any problems or issues or have any questions, do let me know and I'll get back to you. Day 7. Neural network project. Now that we are end of this week, let's do a final project where we're going to do image classification on a Cypher 10. Now this might need a lot of processing power on your computer, so make sure you're prepared for this. The first thing that we want to dive into is applying learned concepts to a more complex project. So that's why we're using Cypher 10. Now why Cypher 10? Cypher 10 is a challenging benchmark dataset for image classification. It contains 60,000 32 by 32 color images across 10 classes. Example, it has airplane, cars, birds, dogs. So unlike the MNIST, Cypher 10 involves more complex patterns and requires robust neural network architecture. Let's talk about building and optimizing a neural network for image classification. The key steps is first pre-process the dataset for training, example normalization and one-hot encoding. Next, we're going to define a neural network with convolutional layers for feature extraction. And then we optimize the network using techniques like learning rate adjustment and dropout. Let's talk about analyzing the model performance and experimenting with hyperparameters. We'll do performance analysis where we evaluate accuracy and loss curves during training. Then we use the test set metrics to measure the generalization. For experimentation, we'll try different activation functions, example ReLU or TANH, and we'll test optimizers like SGD, ADAM, and RMS prop. Next, adjust the learning rate and regularization techniques, example dropout and weight decay. So with all this, let's jump into a hands-on project where the objective is to build, train, and optimize a neural network for Cipher 10 image classification, experimenting with hyperparameters to improve the performance. So first, let's go ahead, create a new file, save it, as day 7 underscore exercise. So let's go ahead and import TensorFlow as TF. Next, I am going to say from TensorFlow dot keras dot datasets, I am going to import the Cipher 10 dataset. Now from TensorFlow dot keras dot utils, I will import to categorical. This will make sure my data is okay. I think looks like TensorFlow. Okay, rest of them is fine. They're just giving me warnings right now, but that's fine. You can ignore them. They are available. Next, I'm going to go ahead and load the Cipher 10 dataset. That I can do by saying xtrain my tuples y underscore train, comma, x underscore test, comma, y underscore test will have Cipher 10 dot load underscore data. So that will load my data into this particular these variables. Next step is to normalize pixel values to 0 comma 1. So I am going to say x train equal to x underscore train dot as type, and I will convert that into float 32 because that's what it needs, divide by 255.0. I will do the same thing for my test data set. So I'm going to say test as type float 32 divided by 255. Perfect. Next thing is we're going to go and do one hot encoding the target values, target labels. So to do that, I am going to say y train equal to 2. As I mentioned, this has all different types of target values, like it can be bird, plane, dogs, all that stuff. So I'm going to say move them to 10 different classes. Same thing I'm going to do for test to categorical y test 10. So perfect. Now I can go ahead and print saying my training data shape equal to x underscore train dot shape, comma, y underscore train dot shape. So that's my training data. Same thing I can say for testing data shape. I'll say x underscore test, y underscore test, and give the shape for that. Now I'm not going to print this out because I know the shape of these. So I'm going to just jump into my next step, which is to define a baseline neural network. So for that, I am going to go to TensorFlow dot keras, and from keras I have models where I'm going to import the sequential, which were used earlier. As I mentioned, these use the different layers in a sequential order, so that's why we use sequential. Next, I'm going to say TensorFlow dot keras dot layers. For creating my different layers, convolutional layer first, so I'm going to use con2d. For my max pooling, I will use max pooling 2d. Next, I need for flatten, I'm going to call flatten. I'll use dense, and I will use dropout. These are all the libraries available, and we've gone through this earlier this week. So if you want to catch up with that, you can look at my previous video. Next, let's go ahead and define the baseline model. To do that, I'm going to say model equal to sequential, and here inside this I'm going to say con 2D, my 32, it's 3 by 3 matrix sizes, activation equal to ReLU. Next I have the input shape. The images that are available is of 32 comma 32 size by 3 layers. So that's what I'm going to set here. Next I'm going to say max pooling 2D. To this I'll say I want to convert that into 2 comma 2. Perfect. Next again I'm going to use convolutional layers 2D, and this time I'm going to say 64 comma 3 by 3. I'm going to use activation equal to ReLU again, and my next layer is max pooling 2D again. For those bits I'm 2 by 2. Once I have this, now I can flatten it, and once I flatten it, now I can use a dense layer, pass it 128, because flatten will give me 128. So that's my input, and I'm going to say activation that I want to use is ReLU, and then I will use dropout 0.5. So I'm going to optimize it to, and then finally my dense layer, which is my output layer, is activation equal to, always use softmax for the output layer. Perfect. Looks good. Everything looks clean. No problems, no errors. Looks good. Now I'm going to go ahead and compile this model. So I'll say model dot compile and pass it optimizer equal to Adam, and loss equal to, as we mentioned, we are going to use categorical underscore cross entropy, and metrics that I am interested in this particular case is, as always, accuracy. So that will compile our model. Now let's go ahead and display the model summary in a nicer table. So I'm going to say model dot summary. That will summarize my model. Perfect. Now that I have the model available, next step is to train the baseline model. So to do that, I am going to create a history parameter variable model dot fit, and to this I'll put all the data. We have xtrain, we have ytrain, next we have the validation underscore split, which is 0.2. next the number of epochs that I want to run it for is, let's say, 10. It might take some time. Batch size that I want to specify is equal to, let's increase the batch size from 32 to 64, verbose equal to 1. So it will take some time to do this training. So next, once the training is done, let's evaluate the baseline model. So I'm going to say loss comma accuracy equal to model dot evaluate and pass it x underscore test, y underscore test, and verbose equal to 0, and that will give me my data. So I can print that out. I'm going to say baseline model test accuracy is accuracy and 0.4 f. Perfect. So that will evaluate and give me my baseline model. Now next, we want to experiment with the hyperparameters. We can experiment with the number of filters and kernel size. We can try to increase the number of filters that we have used to we and or change the kernel size by 5 by 5. We can adjust the dropout rate from zero point 0.5 to zero point 0.3 or zero point 0.7. We can do learning rate adjustment by using learning rate schedulers or different optimizers like SGD or RMS prop. Let's define an improved model. So I'm going to go ahead before even running this. I'm going to write the code so we can run everything together. Improved model. So I am going to use that same model that we have here, call it improved model, and done. No, that's just kidding. So here I am going to use 64 3 by 3. Sorry, instead of 3 by 3, let's increase this to 5 by 5. Activation equal to ReLU. Input shape is 30 to 30 to 3. Max pooling size 2, 2. Count TD. Now I'll increase this to 128. And here also 5, 5. Activation ReLU. Max pooling 2 by 2. Flatten dense. I'm going to increase that to 256. Activation equal to ReLU. Dropout I'll keep the same. No problem. Dense equal to 10. Activation softmax. Now once I have this completed, I am going to compile the improved model with a learning rate scheduler. So for that, I am going to create optimizer equal to tf dot keras dot optimizers dot atom, and I am going to give it a learning rate equal to 0.001. I'm going to say improved model dot compile, and to this compile I'll pass the optimizer, which is my optimizer that I've just defined above. Loss equal to categorical underscore cross entropy, and then metrics equal to, if you remember what we've used, accuracy before, so I'm going to use accuracy. So if you look at this one and the one that you've done here, before we said optimizer is Adam, but here we're saying Keras and we are giving a learning rate of 0.001 and defining our and compiling our model. Now that that's done, let's train the improved model. So use the same code, but I am going to call it, improved underscore history model, or improved model dot fit xtrain ytrain validation split 0.2 epochs. Let's increase to 20. Batch size 64 verbose 1. This is going to take a much more time and much more memory, so you'll have to be patient once you run this. And then I'm going to evaluate the improved model. I'm going to say improved underscore loss and improved underscore accuracy equal to improved model dot evaluate what is this, evaluate, okay, and I'll pass it our values, which is x underscore test, y underscore test, and verbose equal to 0, same parameter that we gave earlier. And then now I can go ahead and print the same thing. Where is it? This is baseline model. Now we have improved model test accuracy, and this is improved accuracy, improved accuracy dot 4f. So that's perfect. Now if you want to do one couple of more things, is we can go ahead and visualize the entire training progress. So for that I can import matplotlib dot pyplot as plt. Now this is not required, but it's up to you if you want to do this. Now plot training and validation accuracy. So of course I like graphs, so that's why I'm doing this. And to this I'm going to pass my improved history dot history, uh, and I can say inside that I like to see the accuracy, and my label here equal to training accuracy. Next, I can do the same thing, plot improved history. I'm going to use val underscore accuracy. That's another parameter in here. And this is my validation accuracy. That's what this is. I'm going to give a title to my plot, and I'll call it accuracy over multiple epochs. I think we're running it for 20 epochs. plt.x label, I will use x axis to show epochs, and I will show the y label to show my accuracy. Next, I'm going to say show me the legend, and finally I'll say plot.show. Perfect. Now I'm going to do the plot the training and validation loss too. I can do that by, let's copy this here, and this one I'm going to say plot training and validation loss, plot improved history loss. I can say training loss improved history val underscore loss, and that is my validation loss, and this is loss over epochs loss legend and show. So let's go ahead with everything completed. Let's go ahead and run this. Python, say day 7 ex.py, and it's going to go through each and every step from starting. And I think I have mistyped somewhere TensorFlow. Perfect. Clear it out, run it again. Looks like I have another error here where I have misspelled the shape. It happens all the time. Shape. Let's see if I am doing it since I copy paste. I'll have the error types. Perfect. Let's hope no more errors. Let's run it one more time. Third time is the charm. And there you go. We have the summary, but it gave me an error here saying that model.fit, it says unexpected keyword argument validation split. Okay, looks like again another typo. Validation split equal to 0.2. Let's make sure that I don't have the same. Okay, let's run it one more time. I have one more error, another typo. Accuracy, let's make sure this is only once. Okay, perfect. Clear it out, run it again. Half of the problems usually is my typos, where I have to rerun my code most of the times. Now it's running for my 10 epochs, so I'm going to pause it here and then come back and show you the results. So it took some time, but as you can see here, it went through my first 10 iterations for my model initially, and right over here, it gave me the baseline model test accuracy of 0.6910. Also, it went through the 20 epochs for the improved model that we created, and we got a test accuracy of 0.7110. As you can see, it's improved. And then finally, our plots where it shows our epochs, which are 20 epochs, and the accuracy, as you can see here, it keeps on increasing above and above the training accuracy. The validation accuracy is right here. I'm going to close this, and it will show me the loss of epochs. So if you see over time, the training loss is reducing because it's getting better and better, and same thing for validation loss here. I'm going to close this, and I hope you were able to get the same output as I do. And if you had any questions or errors or issues other than the typos that I've been doing, I think it should be pretty good. But let me know how does it go. So just to summarize, today we applied concept from previous lessons to tackle a more complex data set. We built and optimized a neural network for image classification. We gained experience in tuning hyperparameters and analyzing the model performance, and we developed skills for experimenting with model architecture and setting to improve the results. And we created the improved model. I hope you were able to follow along. If you have any questions or if you had any issues, let me know in the messages and I'll get back to you.